Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we should be good to go now, I think. So it's a pleasure to introduce Imed Zitouni today. Imed is a former colleague of mine from IBM Research. He just recently decided to make a change and moved to Bing, where he's in the metrics group. He got his PhD at the University of Nancy. After that, he was a research staff member at Bell Labs for a number of years before he joined IBM, where he spent many years actually working on the IBM Tails system, which is their commercial system for doing Arabic and Chinese broadcast news, transcription, and all kinds of interesting analyses there. He's also written a book recently published by Prentice Hall on multilingual natural language processing. And so here he is.
Thank you. Thank you, Jeff, for this. Thank you, everyone. Thank you for coming. So, as you just said, I just joined Microsoft. I'm a colleague, even though that the slides present IBM. So, I'm going to talk about my work in the last, let's say, about 6 years, and mostly on Tails. And I will explain what I mean by that in a little bit, if I can get this going. Okay. This is the outline of this talk. So I will introduce Tails and the information extraction component. That's what I want to focus on today. Mostly I will focus on the mention detection part, the core reference, as well as the relation. I see a typo there. Then I will show how we can transfer a program from one language to another, or to many other languages. So how we make cross-language transfer, and what happens if we don't have enough data to do that, to train a new model. So there I will talk about information propagation across languages. Then what happens when we deploy a commercial system where robustness matter, because the text or the input signal can be very noisy. I will also talk about that, and then I will show how all this technique can be applied to a different domain. And here, I will show how we use this in the healthcare space. And I will conclude my talk. So, I have a video to introduce Tails. It's better than doing that through a slide. So I will try to do that now.
Tails ingests multiple channels of news video 24/7, generating English translations to serve as captions. Tails' video tools capability allows near real-time monitoring of the video as it is captured. Each row in the table corresponds to a show. We see the show's network, the show's title, the language, the start time of the show, the duration of the show, including an indication of how many minutes of it have been captured already. The live column indicates that one show is still being captured, while 6 others have completed processing. Video is processed in 2-minute segments labeled according to how many minutes into the show the segment began. Those shown in blue are fully translated, while light gray indicates segments yet to be captured. Let's look at a segment of Al Jazeera News. Hovering over the segment, the upper left corner shows us a slideshow of the keyframes of that segment of video. Clicking on it, we see the video clip with the automatically generated captions below.
So this is the real-time English translation of the Arabic spoken audio.
We can also use speech synthesis to dub the translation over the original audio. Let's look at a Chinese segment this time.
Good. Today, the evening competition, there managed this. Everyone's attention will use Yang with the United States in this competition.
We can also make captions appear when hovering over segments. These features of Tails video tools allow us to monitor the capture and processing of current video being added to Tails' searchable database.
So these snippets that we saw are important for information extraction, because also one of the idea of this tool is to allow for, let me get this.
I'm sorry, can you search for things in there on a specific
Yes.
topic? Like if you want to find out about, I don't know, Hurricane Katrina?
Absolutely, you can. And actually, we are using OmniFind for that, and that's UCin to do the search. And we do the search at the level of snippets. And it was developed initially to answer the question, who did what to whom? So it's not a regular kind of search. It's a search based on metadata, based on entity, as well as relations between entity. And that's what I'm going to talk about today.
So TAIL ends now. During which year was TAIL? That's the DARPA project, right?
It was initially, so the DARPA project, it's Gale. The tool that IBM built on the Gale DARPA project, and that is trying to sell, to show to customer, that is TAIL. So all the technology behind it, we developed it for Gale. However, we are presenting it under a different framework.
So that's the continuation of Gale in a way?
Correct.
Okay.
Yes.
It's still going on now, or is it finished?
It is still, it's applied to different things. It's applied to healthcare. I will try to talk about that later on. It's one of the joint development agreement we signed with Nuance.
This is the beauty of these DARPA programs, because after you develop the technology, you can sell it.
Yes.
IBM still has all IP.
Correct. So this is the architecture actually of TAIL. So you have, from the keyframe extraction, you have to detect speech and speech detection, then the speaker segment clustering. Then you will run your speech to text, and here we have Arabic and Chinese. You will have your information extraction component on top of speech and also on top of text. And then the name entity transliteration is the part mostly used for machine translation, because you need that for transliteration. And then we have the machine translation part, Arabic to English, Chinese to English. And then you index all this, and you can search them with Lucene or OmniFind.
What about UIMA? We heard it so many times.
Yes.
What is it now?
Yes, what is UIMA? All this so UIMA is a component that help you. It makes the integration of these components very easy. Okay. So you don't want to be aware of what is happening here.
So it's infrastructure.
The infrastructure.
Okay.
It's a kind of middleware. It's an infrastructure. You don't have to worry about what is happening at the different components. Everyone will implement. This is going to be an annotator. That's the way that UIMA uses this component. These are different annotators that communicate with each other. So the advantage of that, I can take the IBM component, and I put Microsoft component. It's going to be instantly. There is no issue. There is no problem of using any. The advantage of this also for our customers is we tell them, this is the architecture we have. If you want to use your own speech recognizer, you want to use your own machine translation, we can do that.
So it's not more like object-oriented program in a larger scale. You get a module, application module by module.
All right, it's XML based, so it helps regarding the interfaces. Let me. How to go from one. Okay, yes, I got it. So here I just wanted to highlight, I'll take a couple of minutes to highlight where my contribution really was in the previous years. I contributed to these different components. So as an example, for the speech recognition part, my contribution was mostly on language modeling, on using rich morphological language for Arabic, putting that into a neural framework for language modeling, using, additional set of features, syntactic features, semantic role labeling, and also using diacritic restoration for Arabic text, even though this was not really successful in improving the word error rate in speech recognition, but still it was an interesting area to explore.
ALECSO, what conference is it?
That's the Alexo, that's the Arabic League. That's the equivalent of Arabic League, that this happen every couple of years in the Middle East. So this one is happening in Qatar, and yeah.
What do you mean by neural network, you're saying? So that's as a technique.
Yes, so the technique was using neural network. There is a paper here. So the idea, the advantage of using a neural network, you can throw into different kind of information, and it will discriminate among those information to help your language model predict better, kind of. And the idea here, so the usual, the suspect language model, the n-grams, we tried to, in addition at the word level, we did it at the morph level because Arabic is high morphologic language. We did also apply the word class. We used semantic role labeler as an additional information there. And that helped not only on speech recognition, but also on machine translation. Regarding the name entity transliteration, that was mostly work on cross-lingual name spelling, normalization, identify name spelling variants, and all that. That helps mostly for machine translation. In the machine translation part, my work mostly was on Arabic to English. And here, the work I did was on the word segmentation level, sentence boundary detection, part-of-speech tagging, and language modeling. And today, I'm going to focus on this part, which is the information extraction part, and that will be the rest of my talk. OK. So kind of in real life, we start with a text like this. There is plenty of tags, and you want to process this data to extract some information from it, OK? So the first step you do is to tokenize the text. So you remove all these tags, and you separate the dots from the tokens, the punctuation as well. You do kind of, and then you do sentence segmentation. You find the sentences. And also, you do case restoration in a sense that here, as an example, you restore the capital letter because it will help you later on detecting person names and all that stuff. Then we do parsing. We run on top of that semantic role labeling. And we do the mention detection part. The mention detection part is to recognize object that refers to an entities, like here Bin Laden, battle, which is an event. I'll talk about that later. CIA, which is an organization. We're also interested on dates. We want to recognize the dates, and so on and so forth. So once we recognize these entities, we want to link the entities that, once we recognize objects, we want to link the objects that refers to the same entity. Like here, I need an information telling me that this token leader and this person named Bin Laden and this pronoun his refer all to the same entity, Bin Laden. I also want to know that this event, killed, short, battle, they all refers to a bombing event. The same thing happened for the city here or a country here, Pakistan, and the same thing happened for the president, which is here. You have here a mentioned president. You have here Barack Obama, and both of them refers to the same person, to the same entity, President of the United States. Now, yes.
To make it look like those are resolving to the actual President Obama,
yeah.
That it's actually to a cluster of mentions, right? Like
yes.
You don't actually link it to natural.
No, it's a cluster. It's a cluster of mentions that refers to that same entity.
Undefined thing.
Undefined things. Yes. Yes. But you know that the president in that text and the person in that text, they are the same. So if you look to the named mentions, you may find the name of the entity. Okay. Once we recognize entity, we want to find the relation.
Just following up on this question, does sort of the absolute resolution happen later, or is that just too hard? Like to maintain a set of things, a set of actual
entities?
Physical entities that things can resolve to, and then globally say, this, and this resolve to this,
correct.
And this, and this to
yes,
this.
That's what we do. Yes,
that comes later.
No, that comes at this stage. I will give detail.
No, but that was at this stage you're talking about right now.
At this stage. No,
but that was just within the text. That was a group of things within the text.
Within the text.
Right, but I'm saying
cross documents.
Cross documents into the actual physical world where everything refers to actual.
That comes much later. That's actually.
Come at all, or?
No, it does, because this is what happened. We index at this level. We index every single document at this level.
Yeah.
And then when you do your search, you are searching for the entity. Let's say I'm searching for the entity Obama. So I'm going to hit all the documents that they have the entity Obama.
That have a mention.
That have an entity, and the entity has a named mention that is Obama.
So you're indexing mentions and you're searching for mentions, is that right?
No, I'm indexing mentions, I'm indexing entity, and I'm indexing relation. But when I said by indexing entities, I have ID for them. It doesn't have to be Barack Obama. It's ID XYZ. It's a single ID.
But there's no sort of database of all the things.
No, I don't have a single database. It's done on the fly based on the named mention within the entity.
Okay.
All right. And after that, we need also to look into relations, what we call relation. And the idea here, if I have the entity killed, which is an event, I have the location Pakistan, I'd like to know that the killed happened in Pakistan and the name of that relation is located at. So we have a set of around 100 relations predefined, and such as manager of, located at, patient of, and we try to do all this together at the relation level. I'll come later in how to do it. Just now I'm trying to introduce the problem.
Are you talking about the time normalization?
Oh, the time, yes. The time normalization, thank you. That's actually the idea. If you have yesterday in the text, the yesterday has to be converted to the exact date. If I have Sunday, May 1st, 2011, if I have today, this is and this happened, today has to be translated, it has to be converted into the exact date. And that based on, if I don't have any information, that based on the date of the document. And if I have some information related here within the text, then again, it's a kind of relation that help me. The relation always, they have a specificity, so they have what we call named, specific, generic kind of relation. And when it's specific, usually it refers to a specific date like this, versus a generic, which can be yesterday, tomorrow, next month, things like that.
So for a fact like Al-Qaeda's leader has been, that is kind of temporal in nature, but not like on the day, right? It's longer term. Is that something that you get?
No, that's not.
It's more like an event.
Correct. Yes, that's an event. Yes. The time normalization is mostly related when last year it happened that someone went somewhere, and that last year you convert it into exact date. And again, the whole idea we have in mind is this is part of the Gale project, the distillation, which is we want to answer who did what to whom, when, and where. And the when is usually date interval from that date to that date. And most of the document, they have this information that you have today's date, and they tell you the article about what is happening last year. So if you need to know what last year means based on the document happening today.
Do you associate the time to the entity? So, for example, 2 years ago, this person had another occupation or vice president, now is president. So how you associate the time with the entity relation?
I don't associate it with the entity here. I just replace last year with the exact date. And if later on I have a query saying that what's the occupation of that person last year, I will translate last year into the exact date, and if both exact date matches, then I will consider this as a hit.
So just one clarification question. So your input is the output of a translation system, right?
Excuse me?
So your input is an output of a translation system. You
no, this is here. I'm this during training. Well, you are talking about decoding. There is two things during training. It is not translation. It's the source language. It is either Arabic or English or Chinese. Okay. During decoding, it can be both. It can be the output of a translation system or a speech recognizer. It can be also the original text.
Okay.
Yes. So how we do mention detection? Similar to many other applications, such as part of speech tagging, Chanker, we consider this as a sequential classifier. And the idea is to process the text from left to right or right to left. It depends on the language you are considering. And for every token, you make a decision whether it begin a mention, it is inside the mention, or it is outside the mention. It's nothing. So, and you run your classifier, and you can take either top n or you take the best answer for that. I'll get into more details in a little bit. So, similar to any other techniques, including speech recognition, you compute the probability or MT in that matter, the probability of the sequence of tags given the words. And for that, we use, again, the Bayes rules, similar to other applications. And what we do for that, we use the maximum entropy framework. And actually, I think that you know this. This is actually was investigated by Della Pietra as well as Berger in 96, 97, where they find an interesting relationship between the maximum likelihood estimates and the mod of models and the maximum entropy models. And this is the relationship that happens here. Actually founding these, estimating these probabilities can be viewed as the maximum entropy and also under the maximum likelihood framework. We choose those that it maximize the entropy over a set of consistent models and maximize the likelihood over a set of models. And here, so the whole idea, what I'm trying to say here is that the maximum entropy model will not assure anything except the evidence, right? So if you have all the data in the world available, you are sure to converge to the perfect model you want. In reality, that's not true, because you don't have all the events it happen unless you have a dead language. If we take the Egyptian languages and we take all the data happening there, and there is no new data happening anymore, and we train on that maximum entropy model, any discriminative training model, we can claim that we have a perfect model. In reality, we live in live languages that evolves and change over time, so that's not a possibility. So that's why we try to estimate the maximum likelihood.
This is a sequence problem. So I think CRF probably would be better.
We tried CRF. We tried Maxent. I believe personally that what matters is the used features more than the approach itself. So, if you look to that's also, this happens in my group, and I have also this idea, maybe I'm wrong. Really, the difference between CRF and Maxent is if you look to the loss functions, if you change the loss function of the Maxent, you get CRF. I understand one is looking to local, the other one, Maxent mostly try to optimize locally, and you hope that will be globally. CRF looks globally, so it's time consuming. It takes more time to do CRF.
You get both tools in the lab?
Excuse me?
You get the tools for both models? Both CRF and...
Truth, you mean?
Yeah.
Yes,
the tools, software too.
The tools. Yes, we do have the tools. Yes. The reason we opted for it's for historical reason as well. IBM believes that they believe that contributed to the invention of Maxent, so they want to keep using it. And since there is no big difference in performance, so it's a good claim to keep using Maxent.
Just to follow up, I don't know this stuff at all, but I feel like Fernando or there's somebody here in Bing that would say that weighted perceptrons here make a big difference. They're faster, they learn just as well, if not better. Have you guys seen anything like that?
The weighted perceptron, so again, all these, including, you can go further than that, and you include into that SVM as well, support vector machine. All these techniques, they are good. They are comparable. That's what I'm trying to say. They are based on discriminative training kind of approaches. Really, the main difference between them is feature use it, the information that you threw into them. So if you go basic information set as or using only lexical input, nothing else, I would assume that you will get comparable results.
Like, have you guys tried it?
I didn't try the perceptron. We tried CRF, we tried support vector machine, we tried the hidden Markov model, the Markovian path. The challenge with Markovian path is like it's very hard to include additional features. The advantage of using Maxent and CRF, it's like easy to implement additional features. So it's for convenience more than for the theory behind it. So here I'll go to the feature use it for this. So we use the context of the word. If I'm trying to predict the tag of this word, so I use the context, the previous words, the next word. I use it in the. We are using Maxent, but also we are using the Markov assumption of Maxent. So we use the previous two tags. We keep the history. That's very important because I saw this in many papers that people telling you CRF works better than Maxent, but their implementation of Maxent is not the Markovian Maxent, and this makes a lot of difference to catch that. Okay, we use dictionaries. We call them gazetteers. So we have huge dictionaries of person names, location, organization, all that. We threw these as features, as a gazetteer information. Document trigger level features. It's interesting to know at what is the document you are handling, and the output of other semantic classifiers. And this is what I mean by semantic. If you have other classifiers, if you have the CRF classifiers, I can use it. I use the output of this classifier as the input to my model. If you are working on a different project, and this has happened, so for Gale, so we worked on ACE, they have a different kind of tags. I will not throw that away. I can use it. I have a classifier trained on that data. I use the output of that classifier and throw it in as a feature.
So
it helps.
Probability from CRF.
Yeah, right. It helps a lot. These, I mean, there is 2 points of measure by doing these kind of things. And two point of measure at the tails when you are already at the 80, it's important.
So what size of the tag dimensionality in that particular application? How many entities?
The training, the data, yes.
The dimensionality.
The number?
The number of classes.
The number of the classes is around 120.
100. Oh, okay.
Right.
And W must be big. So that's very sparse.
Excuse me?
You mean the words in context as
yes.
a feature you use just Engram, maybe
yes.
one word?
We use the context of the two next and the two previous. So five is 5 gram context. We did try something else. Actually, we use also the parser information and semantic row labeling information. So you have the head word information. You have in semantic row labeling, she will tell you more. You have this idea of you have the argument, who is doing the action, who is getting the action. So all this information that we threw as features here, it helps as well on top of the parser.
Yeah, I'm just the dimensionality will be just so large. So you must have some technique to reduce the dimensionality.
Oh, I see. Well, we use. Yes, that's why we use the conditional generative iteration scaling with the Gaussian prior. We need to do that. Yes, we cannot. Yes, I see your point. No, we cannot train on. Yes, true. We need to do that. This is the entities. That's why I'm saying. So this is the set of entities we have. It's a little bit different from ACE, but it covers what we want. So we have 116. And when I said time 3, because we are interested on named mentions, nominal mentions, and pronominal mentions. We differentiate between them. The he is a pronominal, president is a nominal, Barack Obama is named. And this is an idea about the performance. So I know that many people are familiar with what's happening in ACE, and that's why the same technique is used in ACE, and I'm showing the performance here. In terms of precision recall and F measure. So this performance in terms of ACE is very competitive. This same model was ranked in the top in the ACE evaluation, applying it to tails because we have many classes The data is maybe a little bit sparser, all that, so the performance drops a little bit.
So A stands for
Maybe some.
is it part of the GALE?
I think automatic
Content
extraction.
The C is content, E is extraction, and the A is automatic content extraction. It's run by NIST. And yeah, so this is the number of mentions we have, and that's the number of documents we have. Now, we talked about mention. I wanted to do the CoreF part, so how I do that. So I'll be brief here, but we have a paper at ACL for those that they want more details. So actually, really, I take all the mentions here, and my goal is to group them into entities with different IDs. And for that, I use what we call the bell tree algorithm. So I start with the first mention, and then I decide. So I have this, I have all these mentions in here. I take the first one, I put it into one class. And then for the second one, I have two choices, right? The first choice is it belongs to the same class. The second choice will be that it starts its own class, all right? And then when I do that for the third one, again, the different choices I have, even this belongs to the same class, or it starts another class. The same thing in here, all right? So, and again, I use my classifier, my maximum entropy classifiers, with the some threshold because I cannot train on all this. Of course, and we try to. So I try to estimate the probability of linking meaning put it in the same class, and estimate the probability of starting a new entity. Okay, and again, for that, we use the maximum entropy. We are using the same classifier, so the same framework. We don't have to do, and the difference is on the feature we use here. When you do entity, it makes more sense to use, we are using lexical features such as the string match, acronyms, partial match. We are using distant features, how far they are, the two mentions from each other in terms of number of words. Also the mention entity attributes. We did recognize the mention. We know the type, we know the level, we know the gender, we know the numbers. We can use that. And what is interesting, actually, this is kind of, almost most people use this. What maybe make the difference for this, for our approach is using the syntactic features based on the parse tree and the semantic role labeling. And yeah, so compared to what everyone else is using, the performance in terms of CoreF is at this level. Using syntactic features, it helped for English, it helped for Arabic, it didn't help for Chinese. The reason because I don't know how to read Chinese. I don't know, I was not able to debug this. I ran my features, I got that numbers, I said done. I was able to debug this, I was able to debug that, and find out how to improve things.
So such as debug, that means that you see some errors? Or
again, we see the def set, we see what's going wrong in the def set. We try to improve the performance, tune the features to a def set, and then you have a blind test set that this is on the blind test set, right? But again, when you do your training, you always look to some data to see the effect of this kind of feature on that data.
Tuning, kind of feature tuning.
All right, all right.
I assume the Arabic parser is not as accurate as the English one, right?
In terms of performance?
The parser or the syntactic feature
Yes.
should be more noisy on the Arabic than English.
Should be more noisy. That's true. It should be more noisy. However, remember that the fact that it has a high morphology and all that, so you are capturing plenty of information that you don't capture here. So if you, as an example, when you use the context n-grams there, and if you are doing it at the stem level or at the morphs level, you are picking the morphs. So maybe your context get diluted a little bit. However, when you add parser and semantic role labeling, you get additional information that you are losing before because of that details of the morphs. And that helps.
I
the clustering. How do you, I mean, it looks like an exponential search problem. How do you handle that in practice?
Excuse me, repeat again?
I mean, this algorithm you described,
yes.
how if the clusters.
The bell tree, yes.
That seems to be an exponential problem. How do you handle it in practice?
Oh, it's exponential problem. Let me go back. So during training, you have all this. So it's not exponential. It's only during decoding, right? During decoding, the issue you have, if your path is low, you just get rid of it. It's similar to what we do in speech recognition, right? You don't exploit when you do your Viterbi. Even here in the bell tree, you have a kind of Viterbi. So you discriminate, not discriminate. You eliminate the paths that you believe that they will not get you there. It's the same techniques applied here. You are using a Viterbi anyway. It's a bell tree, but think about it as a kind of, you are exploring this path, you have a probability here, you are following that, you are getting another probability here. If the cost of this path is low, I'm not going to follow it.
It's a beam search.
It's a beam search, yes. Yes.
So who provides data?
ACE, there is ACE, the NIST that provides some data. And also for our application, we do have annotators in-house that also, human, yes, that provide this as well.
How much do you need to have? What kind of data? How much
data?
Annotation do you need to get?
Okay, the rules is the more the better, but the more you have the better. But at the level of mention detection, we did find out around million token, you get reasonable, not mentions, text. You start to get a reasonable model. You can improve it. The improvement over that is limited. So if you look to the ACE data was in the range of 400K tokens, and we did add on top of that.
That's not very big. So
it's not a huge.
120 classes. Not on average, each class will have how many samples in training?
So roughly speaking, 400K, if you divide them by 14, so that we are talking about in the few thousand, yeah.
Baseline here. So the baseline is the your model without the syntactic feature, and then you added the syntactic feature in the experimenter.
Yes.
And the baseline is still accent based.
Yes.
And I remember a couple other co-reference resolution papers, for example, from Andrew McClellan's group in UMass. Did you consider those as baseline, or was there some difference in terms of
so there is two techniques. So compared to McClellan, I know we are using similar techniques. The difference is the features, not in on the technique itself. He tried to use CRF. We used Maxent, but that again, I believe it's not a big difference because I believe that the features make the difference there. There is other approaches where they try to do mentions and coref in parallel, try to detect both of them. We didn't explore that path. We know that the overall numbers here is better. We didn't implement that. Because we think that there is a noisy step in the middle. Maybe that's the right way to do a joint approach where you can learn from your mistakes. We didn't explore that. So we did them into two stages. Once mentions are recognized, we keep sometimes, we try to keep the end best, but we didn't try to do the joint approach between mention and coref. Relation. So it's similar to the coref part, is really I have two mentions and I try to find out if I have a relation between them, yes or no. And to do that, I am training a classifier that for every relation, for every two mentions, for all the features that I can fire, I detect does this relation exist or not. And the non-relation is by itself a relation, okay?
So what's the classes, how many types?
The number of them, they are around 50.
50 types.
I will have more details a little bit. So again, I'll skip this. We are using maximum entropy as well, so I discussed that. So what is important here, this is the kind of feature we have. If you have a entity person visited a location, that's a good indication. If you have a person's person, that's also like the father's son. That's a good indication that they are correlated. The organization person, those kind of features that we are using. Of course, for binary features, you understand. For numeric features such as the distance between the two and all that, it's better to bin them. We cannot really use real in maxent. It's better to find bins, and that's how we use them. So again, these features at the parse tree, we find the path from here to here. At the dependency tree, we find the headwords. This is other kind of features. So I have the organization, I have the person, I mentioned that. There is two approaches to do relation. We can do it sequentially, or we do it in a cascaded way. Sequentially, so that we take every pair and we recognize if it does exist or not. So as I mentioned here, in the cascade approach, so you first of all you find, because there is many in the relation anyway, we need to detect the tense, the modality, and the specificity of the models, right? So one way is to separate all of them, to detect one at a time, or to predict all of them at once. And one issue with the relation is the number of class non-relation is huge in the data compared to the entities where there is a relation. And we have to deal with that. That's a big issue.
How do you do that? I mean, you get a sentence here, maybe the whole text.
You have a sentence.
Pairwise?
You have sentence. Yes, you have a sentence. You have mentions or entities within the sentence. And you want to know if a relation does exist or not.
But that's a huge one. You do combinatorial.
No, you do that at the sentence level only.
Oh, understand that. I see. Okay.
Because at the whole document you have the entities, the mention that are grouped in entities that they will help you. But you do it at the sentence level. And even at the sentence level, there is many entities that there is no links between them because they are not related. So you end up, when you are looking to the training data, the number of non-relations label is huge compared to the number of relation. And that's why we did this bagging approach. And the idea is to sample the data, create different samples, train many classifiers, and then if at least n vote, then you call it a relation. So we use the majority vote. That's the known bagging. And also we can use if at least n, then it is a relation. And we do it twice. Actually, first of all, we need to detect, do we have a relation or not? And once we know that we have a relation, then we detect what kind of relation it is. Okay?
You have a binary classifier relation or not first?
Yes.
And then if you have like person, you have subset of the relation to be
yes.
Or everything?
So person, you have, it can be related to, this is the kind of relation we have, right? It can be parent of, because that applies for persons. It can be relative. Then the second stage, you will detect the specificity of the relation. Okay, and now what happened if we apply to this in Arabic? So I only see one Arabic speaker, so just I'll give a brief idea here. If I have, this is the English text, and if you assume that guy is Arabic, you increase ambiguity because there is no vowels. So if you take a text and you remove the vowels, you get something like this in Arabic. Now, there is a lack of capital letters. That also adds another level of ambiguity. And because of rich morphology, few words are attached to each other, like here. All right, so that adds another level. And so a sentence that was initially like this, it becomes like this if you see it from Arabic perspective. And you need to handle that.
Also, this one-to-one correspondence between the letter to Arabic.
Yeah.
Oh.
And not at the letter level, it's at the word level. But it happens that these get glued together. Here you remove the vowels, you remove the capital letters.
What kind of pronunciation is it?
Yes, this is the pronunciation of this sentence is the same. This is English.
I see. Okay.
It's English.
Okay.
It's English that I wrote it Arabic way.
Oh, okay.
So if you cannot read this, that will tell you that's exactly how hard is the problem, because this is English. But that's how Arabic speakers read Arabic. Right? So what we do, we segment the text. I'll go fast for this. We segment the text. We take the text, we separate it into segments, like here. And then we run the same classifier into segments to detect the entities and then the relation. And here I am showing the performance we have on Arabic. This is the feature used. What I want to show here is if I don't have enough data for a specific language, what can I do? I have a rich language. English is rich. We have plenty of resources. We have plenty of annotated data. That is not the case for other languages, such as Arabic. How much time do you still have?
10 minutes or so.
Good. So the idea was how to use rich language such as English to improve other languages, such as here our target is Arabic, Chinese, German, French, and Spanish. These are the language that we want to handle with tails, where we do have some data. It's not we don't have data at all, but the data we have, it depends. So it depends on the language, and it depends. So I'm not going to motivate. I did already the motivation. So what we did is the following. I have a rich set of language, let's say here English, and I want to know how can I have my Arabic model benefit from the English model. So what we do, you train your model, you use all the features, you have the data, so you do the usual things, okay? So that ends up with, you have the English side with all the tags. You have the alignment between the two. You can use even the publicly available like Giza or something, aligner between the two languages if you have the translation of that, okay? And you propagate these mentions to the Arabic side, or in that matter to Spanish or anything else, and you will get your mentions in the target language. Now, if you get that, what you can do with them? You can assume that this is the results if you don't have any data annotated at all in the target language. So you say, this is my results. Or you can say, OK, I will use this as an additional features in my framework. I can build dictionaries from this data. If I have here a huge amount of data, because I don't know, if you look to the European Parliament, where they have plenty of languages, language pair, and they are all aligned, and you can take all, this is a huge, so you take all this, extract gazetteers from that, and use that as a feature. You can also build the model. If you tagged your training data, you will get a training data annotated, so you will use this training data to build the model, and use that model as a feature in your target language. Here, the same example I'm showing for Spanish. So again, I tag the English part, and then I propagate that into Spanish. So the way, as I said, the way we trained it, so we have, if I don't have resources at all, I just use that as the output of my classifiers. If I have some data, then I may use that data to train a classifier and use it as a feature. And here it's gazetteer building dictionaries and using them as dictionaries. And I will compare this shortly. We try this on ACE data because this is publicly available, and we can publish it. So the feature used are lexical with syntax and with semantic features. And the idea we have here, we want to show that the gain in performance decreases with the amount of resources used in the source language. So if you have a donor language, which is here English, you have plenty of resources. If you want to help another language and that language has already interesting resources, you are not going to help it. If that language has poor resources, yes, you will help it. And that's what we will prove soon. So in our case, we use English. This is the performance of English. We have other classifiers. There is no language propagation. And here you will see the performance on Arabic, Chinese, and Spanish, where there is no resources at all in these languages. So it's only propagation. It's only the results from propagation.
That means target language.
Oops. Excuse me?
There's no target language training there.
Yes, there is no target language. This is only English. I have only English data, and this is the performance I get in Arabic, in Chinese, and in Spanish. And the reason here the performance is better makes sense, because Spanish is closer to English than here. Between Chinese and Arabic, it's hard to make a claim because both of them are different, but for whatever reason, Chinese looks...
What is the error rate for English in that case?
80%. 80% F measure.
That's not bad.
Yeah. And this is when we use lexical features. So already we have some data in the target languages. So we see that the performance goes, like for Spanish, it goes to 77. So we are getting close to the 81 of English. Here syntax, and here all the information. So this is, so interesting point here to see Arabic, that Arabic we are less than 1 point behind English.
Yeah, so all you do is that you just propagate them into the training set and pretending that they are correct.
Yes, and the train model on that, and extract a dictionary from that, and I feed that. Yes. So I use the last 5 minutes in here. So all these models that I'm showing, when we show this to customer, and the customer, customer usually doesn't expect to have a clean text, right? Here you have a clean text. You have the system behaving properly. This is the likelihood from the max and the probability for every token, so everything's fine. Here we may get confused between number 1 and number 2, but still, the performance is reasonable. Now, our customer sometimes he feeds text like this. We have English model, but he still feeds this kind of text, and he expects the model to behave properly. And that model that I just described, this is what it's doing. Very bad. Okay, and we have the same text. We have another customer from the finance sector, and this is the kind of data that they give to us. This is actually not the exact data because I cannot show the exact data, but I try to mimic a little bit how it is. And he expected to have a behavior like this. But again, the system doesn't behave the proper way. So plenty of techniques actually are proposed how to overcome, to deal with this noise. We get inspired from these techniques. But what we did here, we first of all, we ran the system to know what is English versus non-English with some probability. We process the text. And then we try to find the SGM tags and all that part. And then, how do we know that the text is English or not English? We are using the perplexity as a measure. Is it in here? So we find out that the perplexity is a good indicator to define if this sentence is a good English sentence or not. And the perplexity is not a binary decision, good or bad. It's like perplexity is low enough, so this is a good English. Perplexity is confusing, I don't know. Perplexity is very, very high. This should be really very bad English. And because of that, we create these different models in the clean text, mixed model in the sense that it's trained on this noisy data. And we have also models that are using only gazetteers, only dictionaries. And this is the performance. So this is the baseline. This is a clean text. We see here how it falls miserably when we train it on, when you decode a text that is not English. But we see that with the technique we proposed, even though we lose a little bit, but that's OK for commercial purpose, because in counterpart, we catch up on this kind of data.
Yes, so in that case, this is bilingual, right?
This is not bilingual. This is English.
If it's not bilingual, how can you do the information propagation?
No. This has nothing to do with the propagation. This is if I'm sorry. I am back to only one language. The information propagation is done.
That requires parallel.
Yes, that part is done. Now I am back to my monolingual part. Okay. So, yeah, I'm on time, I think. So, all things that I mentioned before, the recent projects I worked on is to apply it on healthcare. Healthcare looks to be a very similar problem. Doctors dictate a lot of documents using ASR technology. They also type text. And when they try to send that to the insurance, actually the insurance really worry about what the insurance wants is the ICD-9 or the ICD-10 code that matches the procedures that happen there. They don't want to read the entire document. They are not interested in that. And right now they are this coder, ICD-9, ICD-10 coders that are trying to do that manually. And with this project, we are trying to help them do that automatically. So this is the kind of text you get in a medical. And it will be nice to know that the chest pain is a problem. Probably is a hedge. You need to define, because probably this versus not probably, there is a big difference in the healthcare area. So the terms like probably, not really, not sure, by themselves are mentioned that we need to detect. So we call that hedges. And the relation between this and this, so we have chest pain, non-cardiac, and there is a split atter. So that means they belong to the same attribute, but they are splitted. And here modify by, so this probably modify the meaning of this. So based on, so this is, so again, we do mention detection. It's a sequential classifier. We are on that same classifier to detect relation. And here another example where she's on the medication. The dosage is 40 milligram. It takes by IV, it's push daily. So you have the frequency, the dosage. You need to recognize all those. And based on that, you will give the ICD. Once you have that, it's a trivial kind of to find the ICD-9 code and send that to the insurance.
Who defined that relation to begin with?
Again, you have annotators, you have coders. That's right now they do that job manually. So we are using that data, trying to take advantage of it.
Specify how many
yes. Right. So we have annotators doing that, and we are training model based on that. We are using kind of active learning, all that to expedite the process, but that's the idea. This is also, again, where sometimes the same mentions belong to two different relations. We need to take care of that, because here does not consume cigarette or alcohol. That means does not consume cigarette and does not consume alcohol. So you need to really to get both of it, not only one. It's details, but it's important. So anyway, to conclude, I tried to present end-to-end statistical approach for information extraction and showed how we can, the same technique, apply it to different language. And if we don't have enough resources in the target language, how we can use information transfer across languages. And again, if the receiver target language has enough resources, this approach will not be that nice. So we need to have different kind of resource-rich and resource-poor languages. Then I talk about robustness to noisy text and how we can apply this to other areas such as healthcare. All these gave very competitive performance. In the healthcare space, it's already used in commercial purposes. For Tails, it is also shipped for a couple of customers. And that's about it. Thank you.
Any last questions?
For the healthcare problem, did you find syntactic feature useful?
Syntactic features, they were useful to, not all the syntax is mostly the head word information is very important. That helps to find the split attributes. However, the parser itself, we use some chunking information to know the limit where the chunkers stops. That's it. But also, actually, here our parser is trained on the same kind of data as well. So we are not using a parser on a regular English text.
Okay, let's thank him again.
Thank you.